Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to talk on the module Allotropy of carbon and carbon-based nanostructures from the paper Physics at Nanoscale. So students, let us see what we are going to learn in this module. First, the diamond and the graphite, their structure and properties will be discussed. Second, the C60 fullerene, which is a new carbon allotrope, will be discussed. Thirdly, the carbon nanotubes. We will discuss both the single-walled and the multi-walled carbon nanotubes. Lastly, we will also discuss the structure and the properties of graphene. So let us start with a basic introduction about the module. An assemble of carbon atoms can exist in different distinct forms, differing in the crystal structure with significantly varied physical properties, and this property is known as allotropy. Allotropes of carbon. So students, this figure shows the different allotropic forms of an assemble of carbon atoms. Now here figure A represents the graphite, B diamond, C lanceolate, and the D figure shows the single-walled carbon nanotube, E multi-walled carbon nanotube, F fullerene C60, G fullerene C76, and H shows us the carbon nano horns, and the ith figure shows the onion-like carbon, J shows the graphene, and the K figure shows us the carbon nano ribbons. So now students, let us discuss the historical background behind these allotropes. One such molecule, that is fullerene, which was discovered in 1985, has generated excitement over the last 2 decades. Another example of carbon nanotubes, which are tubes made out of networked carbon atoms with a typical diameter of a few nanometers and lengths of several hundreds of microns. Interest on carbon nanotubes zoomed out after its rediscovery in 1991. The carbon nanotubes, they are interesting in many ways. So the most interesting aspect of carbon nanotubes is the existence of both the metallic and the semiconducting nanotubes, depending on the diameter and how the tube is rolled up. The other two most popular allotropes are graphite and diamond. Graphite is a layered material made up of weakly planar sheets of carbon atoms. They are arranged in a hexagonal lattice structure. The most popular form is the graphene, which was proposed by Wallace in 1947 as a good starting point for studying the graphite is to study the single sheet of graphite. Before 2004, graphene was not existed. In 2004, it was demonstrated in an experimental breakthrough. It is possible to obtain the atomically thin, large, two-dimensional crystals of carbon by a fairly simple technique. In all these allotropic forms, one aspect is common, that is, carbon atoms, they are arranged in different topology by covalent bond with different hybridization, which may be sp3, sp2 or sp, or the combination of these hybrid orbitals. It can be shown that the covalent bonding of graphitic carbon leads to a single set of geometrical rules that relate the shape of a carbon nanostructure with the topology of carbon rings within it. Now students, let us discuss about diamond. Diamond crystal, the figure is shown over here. It is the hardest known natural mineral and has tetrahedrally coordinated carbon atoms which are bonded with each other with sp3 hybridization. So from the above figure, you can see the structure of the diamond where we have C single bond, C bonds which are strong and identical, and the bond angle is 109.5 degree with a bond length of 0.154 nanometers. Most naturally occurring diamonds, now they have the extended three-dimensional network with a crystal structure of face-centered cubic Brevis lattice. And these most naturally occurring diamonds, they are formed at a very high temperature and pressure at depths of 150 to 200 kilometers in the Earth's mantle. Carbon-containing minerals, they provide the carbon source, and the growth occurs over periods from 1 billion to 3.3 billion years. Now let us discuss the properties of diamond. Firstly, it has high melting point due to strong directional covalent bonds, that is around 3350 degrees Celsius. It is extremely hard because it is difficult to break the atoms apart or move them in relation to one another. Next, it has no electrical conductivity because electrons, they are localized in specific bonds. They are insoluble in polar and non-polar solvents because molecular bonds, they are stronger than any intermolecular forces. Graphite. Graphite is another crystalline allotrope of carbon. As discussed before, graphite is the most stable form of carbon under standard conditions. In contrast to diamond, graphite has 3 coordinated sp2 carbon atoms arranged in a honeycomb lattice with layered structure in which the layers of carbon atoms are held together by weak van der Waals forces. Different physical properties of graphite and diamond are manifested due to the different layout of carbon atoms in the lattice of diamond and graphite. Graphite is opaque, metallic, and earthy looking as it is shown in this figure, whereas diamond is transparent, insulator, and brilliant looking. The individual layers of graphite are known as graphene. Now, as you can see from this structure of graphite, where there is a network of coplanar hexagons is formed. In each layer, the carbon atoms are arranged in a honeycomb lattice with a separation of 0.142 nanometers, and the distance between the planes is 0.335 nanometers. Now let us discuss the properties of graphite. Graphite, they are different from diamond. Secondly, they conducts electricity because of delocalized electrons. Next, they are slippery because they can be used as a lubricant. Sheets can be easily slip past each other. Think of a deck of cards. They are kind of same as diamond, that is, they have high melting point, higher actually because of delocalized. For example, it has the melting point of around 3653 degrees Celsius, and obviously it is insoluble with the same reason as we have discussed in diamond. Two forms of graphite. So students, there are two forms of graphite. One is alpha, which is having the hexagonal structure, and the other is beta, which is having the rhombohedral structure. They both have very similar physical properties, except for that the graphene layers stack slightly differently in these two forms of graphite. The alpha form can be transformed to the beta form by mechanical treatment. Similarly, the beta form can be transformed to the alpha form by heating above 1300 degrees Celsius. Fullerenes. Fullerenes, this is a new carbon allotrope, and it was discovered in 1985. In these, the closed cage structure is established by the presence of 5-membered rings. The arrangement of carbon atoms is not planar but rather slightly pyramidalized as a result of a pseudo sp3 bonding component present in the essentially sp2 carbons. Among the known forms of fullerenes, C60 is the most symmetrical and stable fullerene molecule, consisting of 20 hexagonal and 12 disjoint pentagonal faces, where a carbon atom is located at each corner of the individual polygons, which are arranged into highly symmetric truncated icohedrons. There are two bond lengths for C60 molecule. The 6 to 6 ring bonds between the two hexagons can be considered double bonds and are shorter than 6 to 5 bonds between a hexagon and a pentagon, and their average bond length is 1.4 angstroms. In addition to C60, other fullerenes have been reported, such as C70, C76, C82 and C84. So let us now discuss about the C60 fullerenes. That is, it is represented by the carbon atoms bond in the units of 60 atoms, forming a structure similar to a soccer ball with interlocking 6-sided and 5-sided rings, as shown in this figure. It is having sp2 hybridization and extra p orbitals form pi bonds, resulting in electrical conductivity and stronger covalent bonds, therefore stronger materials. So C60, its structure is represented by 20 hexagons and 12 pentagons, and the whole cell or the whole atom is represented by the 7 angstrom in length, and it has a face-centered cubic arrangement as shown in this figure below. Carbon nanotubes prepared by arc discharge evaporation. So students, carbon nanotubes are another allotrope of carbon, and multi-walled carbon nanotubes, they are discovered in 1991, whereas single-walled were discovered in 1993. So, as it is discussed over here that they have been prepared by arc discharge method in a carbon suit whose schematic is shown over here. That is, if we have the anode doped with nickel, cobalt, then we get the single-walled nanotubes, and if we have a pure graphite electrodes, then we have multi-walled nanotubes. A multi-walled nanotube is made up of concentric cylinders with an interlayer spacing of 0.34 nanometers and a typical diameter ranging from 2 to 30 nanometers, and the concentric cylinders, they are held together by van der Waals interactions. The length of single-walled carbon nanotubes is around hundreds of microns. The aspect ratio, that is length to diameter ratio, can exceed 10,000, and thus carbon nanotube is the most anisotropic material. Mostly single-walled nanotubes, they have a diameter of close to 1 nanometer and can be of hundreds of micron length. The structure of single-walled nanotube can be thought of as a wrapping a 1 atom thick layer of graphite called graphene into a seamless cylinder. So now a pair of integers n and m defines how the graphene sheet is wrapped, leading to single-walled carbon nanotubes. So depending upon these combinations, we have 3 different types of single-walled carbon nanotubes. So here the integers n and m denote the number of unit vectors along 2 directions in the honeycomb crystal lattice of graphene. So the 3 possibilities are m is equal to 0. The nanotubes are called zigzag nanotubes. N equal to m. The nanotubes are called armchair nanotubes. Otherwise, they are called chiral. So all these types of single-walled nanotubes have been shown in this figure. So students, let us now discuss the properties of carbon nanotubes. In carbon nanotubes, the carbon atoms are held together by sp2 bonds. Carbon nanotubes are the strongest and the stiffest material yet discovered and existing in nature, with a Young's modulus of around 1.2 tetrapascal and tensile strength of 100 gigapascal, which is about 100 times higher than steel. The electrical characteristics of carbon nanotubes are strongly governed by the diameter and chirality of the nanotubes. So if we have the armchair nanotubes having n equal to m are expected to exhibit the metallic behavior. They have a finite density of states at the Fermi level. However, they may become semiconducting if their diameter drops below a threshold value because the energy gaps in the semiconducting carbon nanotubes scale with 1 by d, where d is the nanotube diameter. Chiral nanotubes, which are having m is not equal to n and m minus n is a multiple of 3, are semiconductors. The band structure of such nanotubes features a very small band gap with a zero density of states inside the gap due to the modest degree of sp2 to sp3 hybridization induced by the non-flat nature of the hexagons on the nanotube walls. Both the single-walled and multi-walled carbon nanotubes show remarkable electrical, transport, and optical properties. In particular, they have been investigated as functional components of energy and gas storing devices, building blocks of nanoelectronic, spintronic, and nanophotonic devices, and medical tools for drug delivery carriers, for cancer treatment, gene delivery systems, and in photothermal therapy. In addition to these practical applications, carbon nanotubes, they are often used as the model systems for the study of various quantum phenomena that occur in quasi 1D solids, including single electron charging, ballistic transport, weak localization, and quantum interference. Graphene. As mentioned before, the most stable state of elemental carbon at ambient pressure and temperature is graphite, which consists of individual graphene layers, each composed of interlinked hexagonal carbon rings tightly bonded to each other, however stacked loosely by van der Waals interaction into a three-dimensional material. Within a single graphene layer, each carbon atom is tightly bonded to three neighbors with sp2 bonding in a plane. As discussed before, the 2s, 2px and 2py orbitals are superimposed to form three new linear combinations which result three lobes of charge reaching outward from the carbon atom at 120-degree angles to each other, all within the xy plane. The remaining 2pz orbital, which points perpendicular to the xy plane, overlaps with 2pz orbitals on neighboring atoms to form an extended sheet-like bonding state that covers the upper and lower surfaces of the graphene sheet. So this figure shows the graphene is a crystalline allotrope of carbon with carbon atoms densely packed in a regular atomic scale hexagonal pattern. Each atom has 4 bonds, one sigma bond with each of its 3 neighbors, and one is pi bond that is oriented out of plane. Now let us discuss the properties of graphene. The ability of carbon to form these highly stable, effective two-dimensional structures is fundamental to possibility to have different carbon-based topological structures which can be realized by distorting this two-dimensional graphene sheet in 3 dimension to form a very rich family of structures. The energy cost to perform these distortions is relatively small. Graphene is a single atomic layer, so it can be bent without changing the in-plane bond lengths significantly. So, in order to achieve the stable distortion from 2 to 3 dimension by bending the graphene sheet into some interesting structures, any dangling bonds at the edges of such a distorted sheet must be eliminated. This can be achieved by wrapping the carbon structure around onto itself so that it forms a closed sheet with no edges. Examples of such structures are carbon nanotubes and fullerene. Another fundamental requirement in a closed graphene-like structure is that every carbon atom have 3 bonds to the neighboring atoms and that the entire structure fold back on itself without any dangling bonds. So students, let us summarize what we have learned in this module. First, the chemical bonds in diamonds, they are weaker than those in graphite. In diamonds, sp3 hybridized bonds, they form an inflexible 3-dimensional lattice, whereas in graphite, the atoms, they are tightly bonded into the sheets, which can slide easily over one another due to weak van der Waals bond between the sheets, making them overall structure weaker. Second, among the known form of fullerene, C60 is the most symmetrical and stable fullerene molecule, consisting of 20 hexagonal and 12 disjoint pentagonal faces, where a carbon atom is located at each corner of the individual polygon, which are arranged in a highly symmetric truncated icosahedrons. Next, we also discussed about the carbon nanotubes, where the carbon atoms, they are held together by sp2 bonds, and carbon nanotubes, they are strongest and stiffest materials yet discovered. Next, a multi-walled carbon nanotube is made up of the concentric cylinders with an interlayer spacing of 0.34 nanometer and a typical diameter ranging from 2 to 30 nanometers. And the structure of single-walled nanotube can be thought of as a wrapping a 1-atom thick layer of graphite called graphene into seamless cylinder. Lastly, we also discussed about a single graphene layer within which each carbon atom is tightly bonded to three neighbors with sp2 bonding in a plane. Thank you.